We're continuing with Chapter 3. In this video, we're going to go through Section 3.10, Linear Approximations and Differentials. Okay, we have seen that a curve lies very close to its tangent line near the point of tangency. In fact, by zooming in towards a point on the graph of a differentiable function, we noticed that the graph looks more and more like its tangent line. So, okay, we've seen that a curve lies very close to its tangent line near the point of tangency. What does that mean? So if you come here, you can see that, and this is in general for any curve, the tangent line to a point on the curve is in blue here, the tangent line to the point is very close to the actual curve when you're right around the point. And this is true in general for any function. Okay, and then it says, in fact, by zooming in towards a point on the graph of a differentiable function, we notice that the graph looks more and more like its tangent line. And so what they're referring to is this here. We have a point on a curve, but if we zoom in, so you can see that the axes are zooming in. You zoom in real close, and all of a sudden it's a line, right? This point here and this point are the same point. You zoom in real close and you can see, like, this would be the tangent line, right? This will be the same thing as the tangent line to this point. This observation is the basis for a method of finding approximate values of functions. The idea is that it might be easy to calculate a value f of a of a function, but difficult or even impossible to compute nearby values of the function, values that are nearby a, f of a, like f of a plus 0.1. So we settle for the easily computed values of the linear function L, whose graph is the tangent line of f at a f of a. So the idea is, if we want to compute a value of this function, an estimated value of this function in blue, at an x that's close to this point, like it's not at a, but something close to a, we can use this linear approximation of the function here, right? It may not be that good of an approximation when you're way out here, but if you're close to the point, it's a pretty good assumption. Now, I remember whenever I went through calculus in college, I would gloss over this section. It just seemed pointless to me. It's like, well, why would you want to do this approximation? Just plug it into your calculator, like plug in, just why would you want to do this? Well, what you're going to see in some situations as you get deeper into engineering or into your respective field, or maybe if you get into research and start publishing papers, there are circumstances where it makes perfect sense that you need to use a linear approximation or some sort of approximation. In real life, if you're modeling things in real life, you can imagine it's not so simple. It's nothing in real life is as simple as the problems that they give in the back of these textbooks, right? Real life is complicated. The equations that you use to model things are complicated with a bunch of different variables. And so what you can do is there's certain situations where it seems almost impossible to solve something like analytically or exactly like per the math, but you can use linear approximations like this and get however close to a that as you need. The computer will calculate something really close to a for you, really close to the point, and so you can get actual solutions. And this is a linear approximation, but we're going to see later in this playlist when we get to series that you can have linear approximations like this, but you can take it steps further and you can do higher order approximations. So not linear, but like parabolic approximations, or even, more than that. So if this section seems kind of pointless to you, just take my word for it that it's a lot more interesting and useful than you might think. Okay, so in other words, we use the tangent line at a f of a. So this is at the point that we know. So imagine, like in a real life situation or in a problem, we can evaluate the function at a is equal to 0 and then f of 0. That's easy. But then what if we need to go a little bit from 0, right? F of 0.1, 0.2. A is equal to 0.1, 0.2, or negative 0.1, 0.2, and then f of, something close to 0, right? That's harder to evaluate. But according to this approximation that we're doing, this linear approximation, the tangent line that we're working with, it's tangent to the curve at the point that's easy for us to work with, a f of a. And what we do is we see that this tangent line, we act like that's the actual curve that, like, we're acting like this tangent line is this curve right near the point. Okay, and so an equation of this tangent line is what? Y is equal to f of a plus f prime of a times x minus a. And this is one of the forms of a line. So remember, if you have a point on the line and the slope, so this is, you have a point on the line. You have, this is, a is x and f of a is y. And then we have the slope m. So like the point slope form, I think, is y minus y1 is equal to m times x minus x1, right? x1 and y1 are the point, m is the slope. Okay, so f of x, which is the main function we're dealing with, is approximately equal to f of a plus f prime of a times x minus a, or just the equation of this is just the equation of the tangent line, is all this is. That's what you're literally saying. You're saying f of x is approximately equal to, this whole function is approximately equal to the function for the tangent line that's tangent to the curve at a. It is this approximately equal to, we're kind of talking about near the point. That's the idea. That's the idea, near the point. This is called the linear approximation, or the tangent line approximation of f at a. And again, we're going to see in the series chapter how we can take this even further, and we can use approximations for functions that are higher order than just linear. Second order, third order, fourth order. So that's great, right? Like the higher order you have, it gives you, it's not only is it more accurate near the point, but it gives you more freedom to go away from the point, which is great, right? If you've got a function that's hard to deal with, or just some complicated real life situation, and you can take something and get a linear approximation or a polynomial approximation, right? Or polynomials in linear equations are easy to work with. That's really useful. So this is the linear approximation, or the tangent line approximation of f at a. The linear function whose graph is this tangent line. So it's this Lx, right? This linear approximation is equal to the function for that tangent line. This is called the linearization of f at a. The linearization of f at a. If you're linearizing a function and you're going to be doing this at a certain value, then what you're doing is you're assuming that the function is the same thing as the equation for this, or the function for this tangent line at a. That's how you're linearizing the function at a. And so what they do here, they say that, so we've got this function, the square root of x plus 3, and we're saying they want to linearize the function at a is equal to 1 and use it to approximate the numbers, so the square root of 3.98 and 4.05. So if a is equal to 1, 3 plus 1 is 4, and we're trying to find the approximations of values that are near 4, 3.98 and 4.05. And again, this may seem trivial. Why don't we just put this into our calculator? Well, first of all, I'm not sure what the calculator is exactly doing in this scenario, but there's a lot more scenarios than you think that where calculators are getting values using like linear approximations like this. You always think of a calculator like this magic device that does everything exactly correct. There's a lot more situations than you realize where the calculator is putting out sufficient accuracy, like in other words, a sufficient number of decimal places, and if it needs to use easier operations, or maybe there's no way of doing something exactly, it's going to use a linear or some sort of approximation for something. So just pointing that out. But this might still seem trivial because, well, I'll still just punch this into my calculator. again, there's more useful applications of this than you would think. And this example is just trying to illustrate the idea of this. But okay, so we're at the square. When a is equal to 1, we have the square root of 4. That's easy to evaluate. That's kind of the idea. With the value of the function at the main point is easy to work with. So f of x is equal to the square root of x plus 3, and we're going to linearize it when x is equal to 1. Well, okay, how do we do that? How do we get L of x? Well, just find f of a. So f of a is easy. It's 2. 3 plus 1 is 4 is 2. F prime of a, well, we have to find we don't plug in a and take the derivative. We have to find the derivative first, and that's what they do here. It's going to be 1 over 2 square root of x plus 3, and then plug in a. And then just put x minus 1. That's what they do here. They simplify, and there's the linearization of that square root of x plus 3 at a is equal to 1. And so what you can do is you can say, plug in x is equal to, so here you would plug in not 3.98, but 0.98, right? Because that's what x is equal to. And here you would plug in 1.05 into this function. This is easier to work with. I mean, the calculator could do both of these easily, but again, we're just trying to illustrate the idea. You know, it would actually take longer to plug this into your calculator than it would this, but that's not the point. So they do this, and for the square root of 3.98, you get 1.995, and for the square root of 4.05, you get 2.0125. Not bad, right? And remember, you can do higher order approximations if you need. If this isn't an acceptable accuracy, we'll see that when we get to the series chapter. If you want more accuracy than this, you can get that, no problem. The linear approximation is illustrated in figure 2. We see that indeed the tangent line approximation is a good approximation to the given function when x is near 1. Yeah, so there's the square root of x plus 3. You know, near 1, looks like a good approximation, at least visually. We also see that our approximations are overestimates because the tangent line lies above the curve. Of course, a calculator could give us approximations for the square root of 3.98 and the square root of 4.05, but the linear approximation gives an approximation over an entire interval. I'm not sure what exactly they're saying here, but I mean, I get what they're saying, but so what? They're saying that the calculator gives us approximations of this, can give us an approximation of these, but with the linear approximation, we get this full function. But I'm not sure what the point of that is. In the following table, we compare the estimates from the linear approximation in example 1 with the true values. Notice from this table and also from figure 2 that the tangent line approximation gives good estatements when x is close to 1, but the accuracy of the approximation deteriorates when x is further away from 1. So we're plugging into Lx, x is equal to 0.9, 0.98, 1, 1.05, 1.123. And remember that our linear approximation was at a is equal to 1, or at x is equal to 1. And so here's the actual value, here's Lx. Whenever we're close to 1, we're really close to the actual value. As we get further from 1, it gets less accurate, but still, like here, when x is equal to 3, we're 2 units from 1. Lx says 2.5. This says 2.449. I mean, this is 2.45. Still not bad. How good is the approximation that we obtained in example 1? So what we just did. The next example shows that by using a graphing calculator or computer, we can determine an interval throughout which a linear approximation provides a specified accuracy. Okay, so this example asks, for what values of x is the linear approximation? So that's the linear approximation, right? That was our Lx, and that was the original f of x. Accurate to within 0.5. What about accurate to within 0.1? And so what they do is they say, yeah, the absolute value of the function minus the linear approximation is less than 0.5, right? Accurate to within 0.5. And then this is just an absolute value inequality. We solve these in algebra, and so you would take this, and to solve this absolute value inequality, you turn it into a compound inequality. And what this is showing is that you have your original curve, and if you shift that curve, just shift it up by 0.5 and shift it down by 0.5, the linear approximation, LX, is in between those two shifted curves. And they show that, okay, it lies above, at least at this point on the curve, the LX lies above the main curve. It extends it, so it intersects the shifted up curve at point Q, and it also shifts the shifted up curve at point P here. So it's those X values, the X value of point P and the X value of point Q. And that's what they show here. When X is between minus 2.6 and 8.6, the linear approximation is within 0.5. And then they do the same thing for within 0.1, and they get minus 1.1 to 3.9. Okay, so linear approximations are often used in physics. In analyzing the consequences of an equation, a physicist sometimes needs to simplify a function by replacing it with its linear approximation. For instance, in deriving a formula for the period of a pendulum, physics textbooks obtain the expression minus g sine of theta for the acceleration of the pendulum, the tangential acceleration. And what they do is they replace sine of theta with theta. And they remark that sine of theta is very close to theta if theta is not too large. And so the pendulum is hanging down, so theta is equal to 0. If you do a linear approximation of sine of theta at theta is equal to 0, that approximation is just theta, or x, right? So they're trying to solve this physics problem. It's too complicated or whatever because of something to do with the math. And they say, okay, well, we can do an approximation based on our experiment. We know that we're not going to be deviating far at all from theta is equal to 0, or not much. We can actually solve this problem if we assume that sine of theta is equal to theta. So this example is giving you an illustration of how, in math, you want to solve for everything exactly correct, perfectly correct. You're trying to solve it for everything analytically. Everything lines up. But in applied math, in physics, engineering, science, you're just using math as a tool to explain phenomena, to make predictions. So it could be very valuable to use a linear approximation, like they're showing here. Another example occurs in the theory of optics, where light rays that arrive at shallow angles relative to the optical axis are called paraxial rays. In paraxial optics, both sine of theta and cosine theta are replaced by their linearizations. So sine theta is equal to theta and cosine theta is equal to 1 are used because theta is close to 0. So they're linearized about 0. But what's cool is you can even go above. Well, again, we're going to talk about in the series chapter, you can do better than a linear approximation if you want. So let's say this wasn't accurate enough. Well, maybe a second order approximation would be accurate enough. And it would take away the complexities that come with the trig function, let's say. Okay, differentials. The ideas behind linear approximations are sometimes formulated in the terminology and notation of differentials. If y is equal to f of x, where f is a differentiable function, then the differential dx is an independent variable. That is, dx can be given the value of any real number, right? It's the independent variable. The differential dy is then defined in terms of dx by the equation dy is equal to f prime dx. Where does that come from? dy divided by dx. dy over dx is equal to f prime x. So you're multiplying both sides by dx. And so now this is the next time that we come across the idea of treating dy dx as a ratio. I've talked about, since we started this playlist, that I wanted to focus in on the idea of treating dy dx as a ratio and the idea of multiplying both sides by dx. And so we do treat dx and dy as sort of numbers here, but I'm not sure how helpful this section is going to be, because we're not treating them as infinitesimally small here. Not for the idea of differentials, for the idea of linear approximations, these are no longer infinitesimally small, dy and dx. Okay, so I just want to point that out. I'm going to make a video at the end of this playlist where, in that one video, we go through all of the sections where dy and dx and Leibniz notation and all of that is mentioned. We're going to go through it in one video. We're going to go through all the sections. But just note here, this isn't an infinitesimally small number anymore. No, neither is dx. But it's confusing because when we take the derivative, it is. When we find f prime x, this is confusing. It kind of is, because if dy dx is equal to f prime of x, these are absolutely infinitesimally small. That's how the derivative is defined. This is the limit as delta, x approaches 0 of delta y over delta x. So this is a little confusing, but you're going to see the way we're treating these in this section, it's confusing. I guess technically, when you look at just this equation as it is, these are infinitesimally small. But as we read through this section, that's not the way the context is a little different in this section. So if you want to see what we've talked about in terms of dy and dx and this dy over dx as a ratio, go watch the video that talks about what does infinitesimally small mean, the precise definition of the limit, not the derivative, of the limit. And around that video, we talk about what infinitesimally small means. I think there's another video that talks about that. Go watch the video where it's the derivative as a function video. That's where we talk about Leibniz notation. That's this notation. And then go watch the video on the chain rule. That's also where this Leibniz notation comes into play. And we talk about treating this as a ratio and what the calculus textbook says about that. But again, I'm going to have one dedicated video at the end of this playlist where we're going to go through every single section of this textbook that talks about that issue, and we're going to bring it all together and see what conclusion we can come to. Okay, but in this context, for linear approximations, we're calling dx a differential and we're calling dy a differential. We're treating dx as an independent variable that we can plug anything we want for dx, and then dy is a dependent variable. It depends on dx and x, right? It depends on x and dx, and that's what it says here. Dy is a dependent variable, depends on the values of x and dx. If dx is given a specific value and x is taken to be some specific number in the domain of f, so dx is given a specific value. What does that mean? Like dx is the distance you are from your main value, right? You're doing a linear approximation of a function at 0 or at 1. That's what x is, right? F prime of x. Dx is the distance you are from that main value on the x-axis. Okay, then the numerical value of dy is determined. Once you pick that x and that dx, well, okay, you have a function. You have to start with a function, f of x. Then you pick the x value, and then you pick the dx value. Then you can evaluate what dy is. Okay, so the geometric meaning of differentials is shown in figure 5. We've got this function on f of x. They call this point P. That's our main point. X, f of x. So if we come here, we have this is our function, f of x. We start at x, and then this is f of x, right? Here's x, and so f of x is the y value of point P. That's the main point. That's the central point, the point that's easy to evaluate. Okay, so now we pick a distance away from x. That's what dx is. So here it says dx is equal to delta x. Delta x and dx are the same thing. So there you go, right? Now all of a sudden this is not infinitesimally small, dx. So you see how the context is a little different? But when you take the derivative, when you take dy dx, when you find f prime of x, most certainly dy and dx are infinitesimally small, at least in that context. Okay, so you have point P at x, f of x. Point Q is at x plus delta x, and then f of x plus delta x, right? That's where Q is. Well, no, here's Q. That's on the curve. P is on the curve, and Q is on the curve. Okay, now what is delta y? Delta y is f of x plus delta x minus f of x. It's this here. That's delta y. This is dy. Dx is equal to delta x. Dy is not equal to delta y. You see, as far as the linear approximation of a function, at the central point, the linear approximation is equal to the function. The linear approximation y value at the main point is equal to the function evaluated at that same central point. We choose a distance from our central point, delta x. That's equal to dx as far as linear approximations go. But delta y is not going to be equal to dy. Okay, so you get this nomenclature. You see how we're going to work example problems, and you see the difference between. You see why dx and delta x are the same? Because they're the independent variable. You can choose them and be whatever you want. Delta y is based on the actual function. Dy is based on the linear approximation. Okay, so they give an example here where you have this function here, and your central point is 2, and then you're going to 2.05. And they say, okay, what's delta x? What's dx? What's delta y? What's dy? And they do the same thing here. So we're going to work examples like this. Okay, and you can also think about how you can get an idea of the error by doing what? What's the error? It would be the absolute value of dy minus delta y. Okay, this last example here says that the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. So they measured the radius of a sphere to be 21 centimeters, and the measurement device had a maximum error of 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? So again, these examples seem kind of crazy, like when would you ever do this in real life? This is just to illustrate these concepts. Okay, so you understand what it's saying, right? We're gonna calculate the volume of the sphere from the radius. But since we have this error in the radius, what is the resulting potential error of the volume we calculate? And also, look, I know it seems crazy, like, okay, well, why don't we just plug into our calculator? We have the formula for the volume of a sphere here, right? Why don't we just plug in when r is equal to 21, and then plug in when r is equal to 21.05, and when r is equal to 21 minus 0.05, and get the actual error. This is just to illustrate the concept. Okay, so you could approximate this if for some reason it was hard to do what I just talked about. If that was difficult, you could approximate it by doing so we have this volume function here, right? This is not linear. We could approximate this function by replacing it with another function, a linear approximation at r is equal to 21. How do we do that? Well, we use this formula here. We're going to take the volume formula, evaluate it at 21, find the derivative of the function of the volume formula, and then plug in 21, and then this will be x minus 21. Well, actually, no, that's not what we would do. You could do that and it would work, but to do it the simplest way, what do we need? What are we looking for? We're looking for, like, as far as the differentials, we're just looking for dy. That's what they're asking, right? The maximum error, like, what is the maximum volume error? So we're just looking for dy, right? If we come here, that question is just asking us for dy. That's all it wants. It's not saying what is a new value of the volume. Like, what is the error reported volume value? No, it's just saying, like, how much are we going to deviate from the actual volume, the perfectly correct volume value? How much are we going to deviate? That's just dy. That's all the question's asking. So how do you do that? You say dv dr. We know how to calculate dv dr. It's going to be 4 pi r squared, and then just multiply both sides by dr. Right, because we're talking about differentials, so you can think about that as a ratio. So we get this. Now all we're looking for is dv. Okay, so now we know what r is, 21. What is dr? We can deviate 0.05 centimeters. So put 0.05, and now you have dv. And if you wanted to, you could plug in negative 0.05, and in some cases that'll give you a different value. You'll get a negative number, but that means it's deviating in the negative direction. So it looks like you get the same value no matter what. But for some formulas, maybe it's not symmetric like that. Okay, now it mentions that, wow, that's a big value, right? 277 cubic centimeters, that sounds big. So if we come here, so this appears to be large, but a better picture is given by the relative error, which is computed by dividing the error by the total volume. So it's dV divided by V. Okay, so if you look at it from that perspective, with the radius deviating by 0.05, so like 0.05 divided by 21, that's 0.24%. And then dV divided by V is the radius is 0.24%, and then dV divided by V is 0.7%. So, but again, I want to caution you, they show this dV over V. When we'll get into differential equations, you'll see formulas like in forms like this. In this context, this is not an infinitesimal. It is not appropriate to say, so like for a differential equation, we would integrate that. No, you can only integrate if you like integration. Again, this might be getting ahead, but this is not, integration is like a cousin of differentiation. There's nothing to integrate here. This needs to be infinitesimally small, like a true dV or a true dy, true dx, for you to look at this like it's a differential equation. In this context, this has nothing, honestly, this has nothing to do, in my opinion, in this context with derivatives. It kind of does, it's confusing, but you could not put an integral here, okay? Unless you see that this is, and you have to know that this is a true infinitesimally small differential, I guess you want to call it. Then you can potentially integrate.